Today, we're going to be detectives. We're diving into a really cool little engineering mystery. It's all about a tiny, hidden flaw in a super common sensor and the honestly beautiful fix that kind of makes our whole modern industrial world possible. Okay, let's just jump right in. Picture this. You've got a massive chemical reactor or some heavy-duty industrial motor. In places like these, getting the temperature wrong isn't just a simple mistake. No, it can be an absolute catastrophe. Being off by just a few degrees could ruin an entire product batch, wreck incredibly expensive equipment, or, even cause a major safety disaster. And that's because temperature is, without a doubt, one of the most critical things you can measure in pretty much any industrial process. Getting it right isn't just important, it's everything. I mean, think about it. You're trying to make sure the windings inside a motor don't melt, or you're trying to control a super sensitive chemical reaction. In either case, precision is absolutely non-negotiable. It's the key to efficiency, to quality, and, most importantly, to keeping everything safe. So if you're going to measure something that important, you need the perfect tool for the job. And to really get our heads around this mystery, we've got to get to know our main character. Now, there are a ton of ways to measure temperature out there. Thermocouples, thermistors, you name it. But for our story today, we're going to zero in on one of the most common and precise ones, the RTD, which stands for Resistance Temperature Detector. The whole idea behind an RTD is just so simple and elegant. It's basically a device made out of a really pure material, and its electrical resistance changes in a super predictable way when the temperature changes. So if you can measure the resistance, you know the temperature. It's that direct. So let's break that down. RTDs are usually made of platinum, and with platinum, as it gets hotter, its resistance goes up. Simple relationship. Now, it's what we call a passive device, which just means you have to send a little bit of electrical current through it to even get a resistance reading. And a really, really common type you'll see everywhere is the PT100. The name tells you what it does. It has a resistance of exactly 100 ohms at 0 degrees Celsius. But here's where our mystery really kicks off. This simple, super reliable device has a hidden flaw, like a little gremlin in the system that can totally mess up its accuracy. And the culprit? You might not guess it. It's the wire itself. Logically, right, you just take two wires and connect the sensor to your controller. Seems easy enough. But look at the equation here. The total resistance your controller sees is the resistance of the PT sensor plus the resistance of the wire. And that's the whole problem right there. You're not just measuring the sensor. See, those copper wires connecting everything, well, they have their own resistance. It's not a lot, but it's there. And your controller, it's a pretty straightforward machine. It can't tell the difference. It just sees one big resistance number and thinks all of it is coming from the sensor. So is this a big deal? Oh yeah. For a standard PT100 sensor, just 10 meters of cable, that's not that long, can throw your reading off by 4.2 degrees Celsius. In a precision environment, that is a massive error. This isn't just some tiny little quirk. It's a fundamental flaw that could totally ruin what you're trying to do. But this is where the story gets really good, because engineers, faced with this problem, came up with a fix that is just brilliant in its simplicity. So here's the puzzle, right? How do you make the controller smart enough to look past the resistance of the wires and measure only the resistance of the sensor itself? And the answer is so surprisingly simple. You just add one more wire. That's it. Look at how the wire as part of the equation is just crossed out now. That one single extra wire literally changes the whole game. Okay, so here's how this magic trick works. That third wire, it creates a second little loop in the circuit. But this loop is special. It doesn't have the sensor in it. It only measures the connecting wires. The controller is smart enough to measure the resistance in the second loop, which tells it exactly how much resistance the wires are adding. Then it just subtracts that number from the first measurement. And what's left behind? The pure, accurate resistance of just the PT100. It's such an elegant piece of engineering. I love it. And for those situations that demand the absolute highest level of precision you can take it even one step further with a 4-wire connection. This setup uses 2 wires just to carry the current and 2 totally separate wires to measure the voltage. It completely isolates the measurement from any wire resistance at all. It's basically the gold standard for accuracy. So, okay, mystery solved. But it's always worth remembering that in engineering, there's always a specific tool for a specific job. Let's just look at the trade-offs here. The RTD, our hero for today, is incredibly accurate and super stable, which makes it perfect for lower range stuff, like those motor windings we talked about. But if you need to measure the insane heat of a furnace, you'd turn to its cousin, the thermocouple. It's not as accurate, sure, but it can handle extreme temperatures and, get this, it's self-powered, which is a pretty neat trick. It's always about picking the right tool for what you need to do. So, at the end of the day, the 3-wire RTD isn't just another component. It's really a story about problem solving. It's a perfect example of how a simple, clever idea can completely overcome a fundamental obstacle to get the kind of precision we all rely on every single day. And that kind of leaves us with one final thought. This whole idea of an elegant fix to a hidden problem, it's everywhere in engineering. What other simple devices or systems that you see every day might be hiding an equally clever solution? Something to think about. Thanks for joining me.